In today's lecture, we would be continuing with our discussion on internet routing protocols. Just to remind what we were discussing in our last class, we talked about autonomous systems which in a sense comprised of a collection of networks and routers which were essentially a part of a single organization. Now, there can be a number of such autonomous systems all around the world. The basic concept behind these routing protocols is that there should be a class of protocols which would be operating within such an autonomous system. Their primary purpose would be to have the routers update their routing table with whatever information they have with them. There are some protocols, a couple of which we had discussed in our earlier class, like the RIP and the OSPF, which are used by the routers which are inside a single autonomous system to update their routing tables. Now, there if you recall, there some kind of broadcast message was used where a router would send some information about some change to the network to all the other routers in the autonomous system. This was possible because number one, the exact topology of the autonomous system was known to each of the routers because it is under the control of a single organization, and number two, the variation or the changes, you can say the changes that can take place in the network are not that frequent. Today we would be talking about one of the most important so called exterior routing protocols, where routers which are sitting in two or more different autonomous systems, they can exchange routing messages. Now, different autonomous systems may actually mean communicating over a wide area network. So, here a lot of, you can say, variation in the network topology, congestion, link status over a period of time are quite possible. So, here the protocols which are used in the interior routing updates cannot be used exactly. So, there has to be some modifications. So, our topic of discussion today to start with is the border gateway protocol, which is one such exterior routing protocol. Now, let us see what BGP actually is. The first thing I just mentioned, that BGP is perhaps the only exterior routing protocols that is used extensively almost everywhere where it is used, and the main purpose of BGP is to allow the routers which belong to different autonomous systems to exchange routing information among themselves, so that their routing tables are kept updated in response to some changes in the network topology. Now, these routing update messages are sent over TCP connections in the network. As a result, as I mentioned, that the router tables get updated. Now, let us see what are the kinds of packets and the other functionalities that BGP supports or provides. Broadly speaking, there are four different types of messages that we have in BGP. First is the so called open message. Now, open means two routers belonging to different autonomous systems, they agree upon the fact that they want to be neighbors. Suppose I am a router, I want to be a neighbor of some other router belonging to some other autonomous system. This can be done by sending an open message. So, this open message is used to open a neighbor connection with another router. This is the essential idea. Similarly, when information about some changes are to be communicated, it is this update message type which is used. Update is used to transmit information about a single route which has undergone some change. This actually means that, say I am a router, I suddenly find that I earlier knew of a route to some destination router, say X, but I now have a better route or maybe a worse route also. Some of the link in my earlier route may have failed. So, I have a modified route up to X. So, I convey this information to my neighbor or the neighbors, whoever are they. So, I am not sending a broadcast message to everybody, I am only sending this to my neighbor routers. Okay. This is done by using the update message. And in order to keep a connection intact or alive, there is a keep alive message type which is used to periodically confirm the neighbor connection, which means that if two routers are neighbors, they must send this keep alive message periodically to each other. So, they know that well the other side is active and is listening to whatever I am saying. Okay. So, this keep alive message keeps the connection up and active. And finally, to take care of the error conditions, there is a so called notify or a notification message which can tell the neighbors about some error condition. Now, this error condition may be in the condition of the link, it can be in connection with the status of a packet which has been received. For example, I have received a packet from a neighbor where I find that there are some errors, that can be checksum error or some header field is invalid. So, in response to that I can send back a notification message to the other side. Okay. And through the notification message, the types of error conditions that can be reported are, firstly, there can be some errors in the message header. This can be with respect to authentication or with respect to its syntax. See, authentication means in cases where we need some privacy, possibly some of the header fields will go encrypted. The receiver somehow finds that it is unable to decrypt it. So, there must be something wrong. So, either in the way it was encrypted or some changes had taken place while the message was being delivered, and syntax, maybe some general error in the header that can again happen due to some error in transmission. Okay. So, message header error will take care of these two things. Similarly, open message error, update message error, these are some errors which take place in connection with the open and update messages. This can be broadly classified into either syntax errors or some options which are invalid, unrecognized options. These again should not occur under normal situations. If there is some error somewhere in transit, something gets changed, then only this kind of errors will occur and will get detected. And in terms of the neighbor connections, there is the concept of a hold timer. Suppose there are two neighbors, suppose this is one neighbor and this is one neighbor, they have a connection between them. Now, the idea of the hold timer is that, say this fellow will be maintaining a timer. So, whenever this neighborhood connection is established, this timer is set. So, the timer actually counts how much time has elapsed since I have last received a keep alive message from the other side. So, if I do not receive a frequently enough keep alive message from the other side, I can declare that somehow my connection is not active right now. So, my neighborhood connection will cease to exist. This is the hold timer expired error condition. Finally, cease, which is an explicit command which can be used to terminate a connection. This command can be used by a router to explicitly ask for closing a connection with another router which is its neighbor. Okay. So, these cease kind of an event also will be going to the other side as a notification message. So, these are the kind of exception or error conditions which can be conveyed through a notification message. Now, talking about the broad functional procedures that BGP supports or handles, there are three broad functional procedures. First is called neighbor acquisition. This I just mentioned that using the keep alive message type, two routers can agree to be neighbors, and this is done by periodic exchange of keep alive messages. So, they start being a neighbor by sending the open message, but subsequently they will have to keep sending the keep alive message to each other periodically, so that the connection remains established. Secondly, once the neighbor is acquired, you must check that the neighbor is reachable or not. Neighbor reachability, to check if the neighbor is still alive and maintaining the relationship. This again is ensured through those keep alive messages. And thirdly, network reachability. See, in BGP, each router, if you look at the routing tables of the routers, they essentially will maintain information about a list of other networks. Suppose I have a packet which is destined to a network N1, so the routing table will tell that which outgoing link to follow in order to reach N1. This kind of information has to be there in all the routers. So, network reachability will tell you that whether you can reach the other networks whose information are there in the routing table. Sometimes due to some error, due to some update messages, you can find that a particular network cannot be reached. So, if that kind of a scenario occurs, you can simply drop that entry from the routing table. So, network reachability ensures that all the networks in the that are listed in the table, it can be reached, and which are the preferred next hops, preferred routes. Okay. Fine. Now, the point to note is that all modern day routers, it can be Cisco or any other make, they will support BGP, because BGP has emerged as the de facto exterior router update standard. So, this is the fact that we see all around us, but one thing you should also remember, that not everybody runs BGP. Typically, the routers that are managed by the internet service providers or ISPs, they actually run BGP. For example, I may be referring to me as an individual, or I may be referring to myself as an organization. Suppose I have obtained a network connection, internet connection from an ISP like VSNL. So, I get a connection from VSNL. So, actually what does that connection mean? It can be a dial up connection, it can be a leased line connection, whatever may be the connection to my site. Ultimately, my connection will get terminated into some router port in the ISP side, and that particular ISP must be running BGP, so that it can keep its table updated with respect to changes that are happening to the outside world. Because if the router through which all my packets are going out is not updated regularly, there can be a problem. That means I may not be able to route my packet in a proper way. So, the ISP routers must always be running BGP. But however, the organizational networks, there can be routers inside an organization also, they in many cases do not run BGP. This is of course a choice, it is not mandatory for them to run BGP. In that case, what they do, they would rather rely on the ISP's routers to route the packets to the outside world. It means suppose I have an organization. Inside my organization there can be 2 or 3 routers, but none of them is running BGP. Rather, all our packets which are destined to an outside network will be sent to our ISP router, and it will be the responsibility of the ISP router to route it properly. So, it is not that a router inside our organization will be running BGP and will take a decision that where to send it from our organization. See, this kind of a solution is very typical where an organization has a single or very few, maybe 2 connections to the outside ISPs. So, the internal router really do not have much option. They will have to forward it to the ISP in any way, and since the ISP router is running BGP in any way, so you may not run BGP inside. Okay, this is the basic reason. So, under this condition, the default route of the router which is inside will be set to the ISP router. So, if the destination does not match with an internal address, it will be directly sent to the router which is outside. Okay. Now, let us shift our attention to a slightly different topic. Now, if you recall, when we had talked about TCP IP earlier, we had basically talked about the IP version 4. We said that it is the most commonly used protocol that is being used in the network layer protocol in the internet. IP version 4 is basically a datagram based service which takes the responsibility of routing the datagrams from one source to a given destination. So, each of the IP layers in the intermediate nodes take decision typically with respect to the IP address of the destination, that means where to forward the packet to. Now, we had seen that this IP version 4 basically the way we address the hosts, it is a 32-bit addressing scheme, and the classical IP addressing scheme, they assumed that you break up the total 32-bit address space into 2 parts. One part will indicate the address of the network and the other part will indicate the address of the host or the computer within the network. Now, there are 3 classes, as you know, class A, class B, class C, depending on the sizes of the networks you choose to use. There are other classless options also. You can go for variable length subnet mask, you can go for classless internet domain routing. So, these are options available to you, well, which do not deviate from the IPv4 addressing scheme, but rather try to provide us, you can provide a mechanism for more efficient utilization of the address space, of the available address space. Now, it was long felt that IP version 4 has already long lived its life. Now, the time is ripe to go for a change or some modification to a next higher version of the protocol. This IP version 6, which is the latest version of IP which has become means available as a standard since a long time. So, let us first look at this IP version 6, what it is all about, then we shall be talking about the present status, where are we with respect to IPv6. Now, I just mentioned that this IP protocol which we use in the internet so widely today. So, the protocol which we mostly use is the classical IP version 4. We shall see shortly that IP version 4 as it is existing, they suffer from a number of drawbacks. Therefore, there is a need to enhance the capabilities of the protocol so as to overcome this drawback. So, this IP next generation, which is sometimes also called IPNG or in short IPing or IPv6, this is what has been proposed to to address this issue. The issue that this IP version 4 is not capable of handling future needs. There are some disadvantages which you face with IPv4, how to overcome them. So, let us see how these are done. First, let us very critically look at some of the problems that IPv4 faces. Most important problem that IPv4 faces is the limited address space. We have only 32 bits available to us for addressing a node, and as we see today, as we see the state of the internet today, we see that already there are close to billion computers that are connected, and 32-bit addressing is grossly inadequate. We have formulated or framed a number of different ways to efficiently try to utilize the available address space, but still the time is very near where we will be absolutely tied up. We will not be able to expand the networks further because of our paucity or scarcity in the available address spaces. We use protocols like DHCP and other protocols to again efficiently utilize the available number of addresses that we have, but still these are all stopgap arrangements. We have to have some solution. This is of course one drawback. There is another very big drawback. There are many applications which demand real time response. Now, you see that nowadays there are a number of applications like video on demand, online audio, then means you have IP telephony. There are these kind of applications which demand real time response, but in the classical IP version 4, as I had mentioned, that IPv4 is based on the datagram technology. A packet is sent independently, it can follow any available path. Suppose I want to send speech signal as a sequence of packets, there is no guarantee that my speech signals will be arriving at the destination means uniformly spaced in time. There can be unequal gaps between the different parts of my voice speech. Some packets may get lost in transit, some packets may be reached out of order. So, we can, so here in terms of the response, we may hear some gaps in between speeches sometimes. So, IP version 4 does not do much to cater to this kind of applications. They say that if it is real time application, if you do not find a packet, simply reject it. It is perhaps the best solution. So, it is better to have a small gap rather than hearing this voice 1 second later after something of the future has been spoken out. So, that is not acceptable certainly. So, real time response will demand that somehow you should avoid changing routes frequently, because if you change route frequently, your real time response cannot be guaranteed. And again, the third thing is that IP version 4 has a classical 2-level addressing, network and host. These simple 2-level addressing may not be inadequate for modern day applications, as we will see shortly. There may be the need for having more number of levels in addressing. Now, some of the main features of IPv6, of course, something are there which are common to IP, like it is also based on datagram technology, it is a connectionless technology. Each packet or datagram will contain the destination address and will be routed independently. Secondly, just like IPv4, the packet header will contain the maximum number of hops a datagram can make. So, at every hop the count will be decremented by 1, as soon as it reaches 0 the packet will be discarded. This is exactly what is done in IPv4. So, here also something very similar is done. Some of the other general characteristics like fragmentation, reassembly at the final destination, these are also kept the same as compared to IPv4. Okay. Talking of the new features, the most striking feature is the address size. Here from the 32-bit IPv4 address, we are moving on to a 128-bit address in IPv6. So, how much or how big is this 128-bit address space? Let us try to have an idea. See, 32 bits means 4 billion, 2 to the power 32 approximately, this we know. But how much is 2 to the power 128? Can we have a rough idea about that number, that figure? Let us see. If you compute 2 to the power 128, it comes to close to 6 into 10 to the power 23 addresses per square meter. This is not the total. If you compute the whole circumference of the earth, okay, if you take the whole circumference of the earth, then with this 2 to the power 128 different addresses, in every square meter of the earth surface we can have 6 into 10 to the power 23 addresses assigned. Okay, so you can imagine how huge is this address space, and what this number means is that, well, approximately you can assign one address to one molecule on the earth surface. Okay, this is a staggering number. That means every molecule on the earth surface can be assigned an IP address. 2 to the power 128 means this much. So, most likely in the foreseeable future, if we start using this 128-bit addressing scheme, we shall not run out of addresses anymore, at least for the coming 10 or 20 years. Okay. Now, there are some other changes also, some new features of IPv6, because recall in IPv4 we had a very well defined header. So, all IPv4 packets use that same header, but in IPv6 the concept has become slightly different. IPv6 does not use a single header, but a series of headers. So, all the headers are of fixed sizes. There is one header which is compulsory, which is called the base header. Following the base header, you can have 0 or more extension headers. Now, extension headers are something which may or may not be present in a packet. Suppose if a packet needs to be fragmented, then you need a fragmentation extend header. If you want to have some kind of encryption facility in a packet so as to provide message security or secrecy, then you can have a security extension header. So, these are the kind of extension header which are very specific to the needs that you have. But in addition to that, we have one compulsory base header which will contain the basic information that we always require with a packet. Okay. So, this is the idea, one base header followed by 0 or more extension headers. Okay. The third thing is that IPv6 supports real time traffic, which means there is a facility to allow a pair of stations to establish a high quality path between them. For this purpose, again you have a special purpose extension header. Suppose I want to establish a path with a destination. Between us, I want a 64 kbps dedicated bandwidth. So, a priori I will try to establish a bandwidth where each of my intermediate nodes will give me a guarantee of this 64 kbps bandwidth. So, once this path is established, I know that I have a guaranteed route where each of the nodes who are sitting in between, they will be guaranteeing me my required bandwidth. This is called quality of service guarantee. Okay. This is guaranteed, and once such a path is established, all datagrams will be forced to flow through this path, because unless the datagrams flow through this path, the guarantee of the quality of service cannot be ensured. And the last thing is that you have increased flexibility in addressing, we will see it very soon. There are some new ways of addressing hosts which have been introduced, which was not present in IP version 4. Like for example, a new concept called Unicast address has been introduced. See, Unicast means, suppose you have a number of computers. These computers can form a group. You can define a Unicast address group with this set of computers. Suppose a packet arrives to this group with an Unicast address. What this will mean is that this packet must be delivered to any one of the members of the group. This is unlike broadcast, where the packet has to be sent to everybody, but here it is not that way. Here the packet needs to be delivered to exactly one member of that group. See, this kind of applications are very frequent nowadays. We talk about internet search engines, we talk about the internet mail services and so on. Well, if you look a little carefully at these websites, you will find that each of these websites will correspond to multiple IP addresses, which means that there are so called mirror sites available. The name may be same, the domain name may be same, but there are mirror sites. So, when I want to contact such a site, so it would be very nice if I can have this Unicast addressing scheme, so that whatever I am going to send, it will be reaching my nearest mirror. Okay? This is the idea. And also you can have dynamic assignment of IP addresses very easily. This is of course a new feature which has been added. So, here as and when you need, an IP address can be assigned to you in a dynamic way. So, these are some new features which IP version 6 has introduced. Now, let us see the IPv6 datagram format, how it looks like. Well, as I had mentioned earlier, that an IP datagram will always begin with a base header followed by 0 or more extension header, and finally you will be having the data part. This data part will be coming from the layer on top of IP. Typically on top of IP you have the TCP layer. So, the TCP layer will be sending a chunk of data to IP for transmission. So, actually this data is sometimes called the transport layer protocol data unit or PDU. So, this data that we are showing in this diagram at the end, this is the transport layer PDU. Before it you have a mandatory base header, but this extension headers are all optional, you may or may not require. Depending on what you are trying to do, this extension headers may be present, may not be present. And the thing to note is that the base header has a size of 40 bytes. In fact, all the other extension headers are also of the same size, 40 bytes base header. So, let us see what does the base header contain. The base header contains some fields. Version, for IPv6 this version field will contain the number 6. Priority, well, you can assign priorities to your packets. If a packet has a higher priority, if it is assigned a higher priority, then the routers will give priority to your packet for transmission. Then you can have something called flow level. This is used for flow control. Payload length, this is the total size of the packet. Next header I shall be talking about. Hop limit, this is what I had mentioned earlier. This field is initialized with the maximum number of hops the packet can take. So, whenever this packet hops from one node to another, the hop limit or hop count gets decremented. As soon as it reaches 0, the packet is discarded. The idea is that this hop count is set to some maximum value and the nominal path length should not exceed that. If due to some reason the path length actually exceeds it, this will mean that either the packet was somehow routed in the wrong direction or it has somehow gone into a routing loop. It is circulating in a circular path in loop. In addition, we have the source address and destination address, both are 120 bits. So, this total header size is 40 bytes. Out of them, the source and destination addresses will consume 16 and 16 32 bytes. The remaining 8 bytes are for the other headers. Now, let us see what the other headers, their sizes and their functions are. Version, I told you it will contain the value 6 because it is IP version 4. This is a 4-bit field. 4-bit, well, to represent 6 you may need 3 bits only, but these 4 bits have been kept for future expansion. Maybe sometime later we may be having version 8, version 10 like that. So, 4 bits are kept. Priority, as I told you, this specifies the routing priority. Flow level, well, this I am telling you what this actually means. This ensures some sort of flow control and quality guarantee. This field is used with applications that require performance guarantee. See, suppose I go back to the example I said, I need to establish a 64 kbps link with the destination. So, when the path gets established, so all the intermediate nodes are informed about my, I could say, my willingness that I want to establish a path through you and I want a guaranteed bandwidth of 64 kbps. Now, I also mentioned that in order to have this feature, all the datagrams must follow the same path. So, essentially we are talking about something which is similar to a virtual circuit. So, although we are talking it in terms of a datagram, but since we are restricting the path has to be the same. So, it is effectively something like a virtual circuit, and this flow level is actually something like a virtual circuit number. So, if the packet contains that number, every intermediate node on the router can find out, well, this is the flow level number 10, which means I have to forward it to this node. So, this is very similar to the virtual circuit number actually. And the next field is the payload length, which is 16 bits, 2 bytes. This contains the total length of the extension headers plus the data part. Since it is 16 bits, the total size of the datagram can be 64 kilobytes. Next header, it is an 8-bit field. It actually identifies that if there are some extension headers following, what is the type of the extension header? It identifies the type of information that immediately follows the current header. There can be a number of different header types that follows the present base header. It is like a pointer to the next extension header. The next header field essentially works as a link. It is like a linked list. The headers are maintained like a linked list. So, this diagram will show you this. Suppose you have, in the first example, you have a packet with only the base header, nothing else. So, you have the base header followed by the data, which is the TCP data, the data which has come from the TCP layer. So, in the next header field, the value TCP will be stored. This will mean that the next, whatever is following the base header is the TCP data. But in the next example, say we have a scenario where in addition to the base header, we have another header which is a routing header, which is used to establish a high quality path, for example. So, in this case, the base header will have the next pointer as of type route, the route header will have the next one of type TCP. So, essentially what it means that all the headers are like the nodes of a linked list, and there is a connection from one to the other. Okay. So, starting from the base header, you know that what is the next type of the header. If there is a header, you process it, otherwise you can straight away go to the TCP data and so on. So, hop limit I have mentioned, and source destination address also I have mentioned. Now, IPv6 extension header, there are a number of different header types possible. Some of these have been shown here. First one is the routing header, which provides the so called source routing. Source routing means the source can specify the path the datagram has to follow. Suppose I am sending a packet to a destination and I know that if the packet follows this particular route, then it will be good for me. There will be less congestion, the packet delivery speed will be higher. So, I can specify that please follow this path. So, if it is a source routing packet, then the IP layers in between, they will not try to carry out any routing decision on their own, they will simply follow my instructions which I have sent along with the packet. Okay. So, you have a so called hop by hop options header. So, here you can specify a number of special options. So, I am not going to details, but the number of options can be varied. So, these options can be processed at each hop. So, in case the packets get fragmented, you have fragment header. So, for fragmentation and reassembly, the fragment headers are used. For security applications, you can have an authentication header where packet integrity and authentication can be taken care of. That means to verify the source of the packet, to verify that the packet has not been modified. And as I had mentioned that all the extension headers are chained in a linked list by using the next header field, which is present in every header, base header as well as the extension headers. They are connected as a linked list, right. Okay. Regarding fragmentation, well, IPv6 and IPv4 fragmentation is similar, but in IPv6 the only difference is that fragmentation information is not stored in the base header, rather it is stored in a separate fragment extension header. Now, if in a packet you find that the fragment header is present, this means that the present packet has to be a fragment. So, just by looking at the presence of the fragment header, you can actually confirm whether the packet corresponds to a fragment packet or not. Okay. And well, if a packet gets fragmented, then the base header gets copied into all the fragments. The optional fragment header along with the offset and other information will get appended or added to the different fragments, and that is done exactly in the same way as in IPv4. So, there is not really much difference out there. Talking about IPv6 addressing, how we specify address of a host. So, unlike IPv4, here you do not have any defined classes like that ABC. Rather, you can specify a prefix length with each address, like you can say CIDR, classless internet domain routing. So, you have seen CIDR provides enough flexibility. Depending on my requirement, I can specify a prefix length and the last few bits I can use as my host addresses in my network. Okay, that can provide you with a lot of flexibility, but here it is more general, as we shall see very shortly. And in terms of the types of addresses, there are three types. One is of course unicast, where the destination is a single computer. Multicast, where the destination may be a set of computers, but they may not belong to the same LAN. They may possibly belong to different locations. Now, if it is a multicast address, then the packet will be delivered to every member of the set. Okay, this is multicast. Now, in contrast, I just mentioned you can also have Unicast, where again you also have a set of computers, and Unicast, you can say address, all the computers must have the same address prefix, and packet will be delivered to exactly one of these computers. Okay. So, this Unicast, as I mentioned, this is typically used to support replication of services or mirrors in systems. Now, IPv6 address is normally expressed in the so called colon hexadecimal notation. The dotted decimal notation like IPv4 will be too long to use. Colon hexadecimal notation works like this: the whole 128-bit address you divide into groups of 16 bits and write each of them down separately in hexadecimal, and instead of dot you use a colon to separate them. This is an example of an IPv6 address. Now, in practice you will find that most of the addresses you will have will contain a lots of zeros like this. Now, it is possible that there are a set of consecutive, you can say, hex blocks which are all zeros. So, in this case you can write it in a compact notation where all these consecutive zeros can be written as double colon, okay, 2 colons, written as 2 colons. So, this is a compact way of writing this down. And you can have aggregate global unicast address. This means that the total IPv6 address you can divide as follows. Well, you usually start with 001, indicating that it is a unicast address. All unicast address will start with 001. You can have top level aggregation. This can refer to the top level internet service provider. There are 13 bits for it. You can have next level aggregation. This can be country level internet service provider. You can have site level aggregation. You can have city based internet service provider. You can have a number of different levels of hierarchy, and at the end you have 64 bits to represent your computer. So, what has been suggested is that these 64 bits can be used to represent MAC addresses directly, so that there is no chance of replication. Two computers can never have the same address. So, by these kind of hierarchical facility you can very well, or means you can assign the addresses in a very structured way, and simply by looking at the address you can very easily know that to which hierarchy your address belongs to. You can know of your country, which ISP you belong to, and so on. And there is something called IPv4 mapped IPv6 address. This will allow a host that supports both IPv4 and IPv6 to communicate with a host which understands only IPv4. Here there is a convention of the address. The first 80 bits of the address will be zeros, followed by 16 ones, followed by a 32-bit IPv4 address of that machine. Okay. So, the IPv6 address is basically derived from the IPv4 address. This is how you write. First there will be a sequence of zeros, then there will be a sequence of ones, then the actual IP address, 32 bits. Okay. After that you can have something called IPv4 compatible IPv6 addresses. Here a host supporting IPv6 can talk IPv6 even if the intermediate routers do not support IPv6. So, this uses tunneling. The IPv6 packet can tunnel through an IPv4 network. Here the convention is that 80 plus 16, 96 zeros are there in the beginning, followed by the IP for IP address which is 32 bits. So, this looks like this. You have the IPv6 host, there are a number of intermediate routers which understand only IPv4. You use tunneling where the IPv6 packet or datagram is treated as the data. You create an IPv4 datagram on top of it and send it here, here and here. So, the final IPv6 host will take out the IPv6 datagram and will be extracting the data from here. This is typically done automatically by the OS kernel which supports IPv6. And to talk about the transition, well, you can have a system where you have both IPv4 and IPv6 protocol. You can have tunneling which you have just mentioned. you can have header translation, where a gateway will automatically translate an IPv4 header to an IPv6 address. These are the different kinds of options that you have when you want to do a transition from IPv4 to IPv6, but the modern day scenario is that very few organizations have actually moved on to IPv6 because of some compatibility issues. Most of the IPv6 networks are confined to labs, but the transition has to take anyway. So, we have to gear up for the future and find out that when earliest we can carry out the transition. So, with this we conclude our lecture. Now, let us quickly look through the solutions to the quizzes of our last class. The questions are fairly simple. What is a connection oriented protocol? Basically, this means that where first a connection is established, then the packets are sent. And a connectionless protocol, where you do not establish any connection and packets are routed in an independent way. Okay? This is basically virtual circuit and datagram kind of approach. What is the difference between direct and indirect packet delivery? In direct packet delivery, no router is encountered in between, but in indirect, the packet may have to go through intermediate routers. This is the difference. How is the default route specified in the routing table? By specifying as the address 0.0.0.0. That will mean default. What is the problem if we use only host specific routing and no network specific routing? The problem is that there has to be an entry in the routing table corresponding to each host, which can become very big. The routing table can become very large. That is why we have to go for network specific routing, because in host specific routing, if there are 1000 hosts, then the routing table has to contain 1000 entries. Okay. G and U flags, what do they signify? G means destination is in another network, U means the router is currently up and running. Difference between interior exterior routing protocols, we have told this many times. For interior protocols, router are in the same autonomous system, exterior they are in different autonomous systems. What is an autonomous system? They are a set of routers and networks which are managed by the same organization. How do routers update information in RIP? They use distance vector routing. By using the distance vector received from the neighbors, they update their tables. How do routers compute path in OSPF? Well, OSPF uses the shortest path algorithm, Dijkstra's algorithm, to compute shortest path, because OSPF, every router has complete information about the network, they can optimally compute the shortest path. Which paths do the packet follow in OSPF? Well, in OSPF, from each router it follows the next hop according to the paths computed in the router, because the Dijkstra's algorithm computes the shortest path, but it only keeps information about the next hop with respect to the shortest path. And regarding questions from today's lectures, these are some questions. What are the 4 types of BGP messages? How is a BGP connection between 2 routers maintained? What are the main functional procedures in BGP? Why is IPv4 not suitable for supporting real time traffic? How are the multiple headers in an IPv6 packet kept track of? How does IPv6 attempt to support real time traffic? What does the payload length field in IPv6 header signify? What does the next header field signify? In IPv6, how are the fragments kept track of in case a packet is fragmented? What is Unicast addressing? How can you use tunneling to send an IPv6 packet over a IPv4 network? So, with this we come to the end of today's lecture. Thank you. In this lecture, I would like to touch upon a very important concept which is used widely in the internet nowadays. You must have heard about the term client server concept, client server programming. In fact, most of the internet applications that we see today, that we use today, they are based on this kind of client server programming. So, first I try to explain what this client server programming concept is all about, then we shall be specifically looking at some of the applications of the internet. So, client server concepts and some of the applications are the topic of our discussion today. So, first see what the client server model is all about. This is a standard model for developing network applications today. Now, as the name implies, there is the notion of a client, there is the notion of a server. The basic idea is that a server is a program, or which is sometimes called a process. A program in execution is called a process. A server is a process which is continuously running and it wants to offer some services to clients. My purpose of telling all these things was to give you a rough idea about what this client server concept is all about. And I told you all the internet applications that you see, they are all based on the client server concept. Now, I would start with one of the most important applications, which well in itself is not an independent application, but is used by many other practical applications. That is the so called domain name system or DNS. This you may have heard. This is a very important service which is provided in the internet, in LANs, in different areas. Basically, the domain name system is a global database system for internet addressing, mail, other info. See here, this need not be restricted to internet addressing mail, it can refer to World Wide Web, Telnet, FTP, any kind of application you use today, you typically use a name, you do not always use an address. The purpose of the DNS essentially is to convert from a name into an address. Okay. So, this is how it works. Now, the advantage of using DNS is that, see, using names rather than addresses is much easier to use, easier to memorize. Like for example, I am giving you one practical you can say example. Say the mail server of the Computer Science and Engineering Department of IIT Kharagpur, that can be referred to by a name CSE. The full name is cse.iitkgp.ernet.in. Well, you are familiar with names of this type. Now, this kind of a name is easier to memorize, but I also know that the IP address of the CSE machine is 144.16.192.57. Of course, you cannot remember many such addresses with numbers, you may tend to forget, but using names is much more easier because it is more English like, more easy to memorize. Some questions from today's lecture. What is an iterative server? What is a concurrent server? Which of client or server must start first? What are the components of a socket? What is a domain? What are named and NS lookup? How does recursive name resolution works?